As we look out into the vast expanse of the universe, we can't help but be amazed by its enormity. The stars we see twinkling in the night sky are only a small fraction of the billions upon billions of stars in our Milky Way galaxy, which is just one of the billions of galaxies in the observable universe that spans an incredible 46 billion light-years in every direction. This vast and intricate universe traces back to a single moment about 13.8 billion years ago known as the Big Bang. Then, the universe emerged as a hot, dense and rapidly expanding state, creating the foundation for the universe we know today, governed by the laws of physics and filled with matter and radiation. While it continues to expand and evolve, one question remains: when and how will this all come to an end? Albert Einstein was among the first to ponder the fate of the universe. He believed that gravity would keep the universe static, but his theory was challenged by Edwin Hubble's discovery that galaxies were moving away from each other, indicating the expansion of space and time. This led Einstein to introduce the concept of the cosmological constant, a repulsive force that would counteract gravity. Back in the 90s, experts believed the universe would either stop expanding and contract or keep expanding forever. Although gravity would cause the expansion to slow down, this was not observed. The universe was expected to decelerate. However, in 1998, scientists made the shocking discovery that defied all expectations. The universe's expansion was accelerating instead of slowing down. The Hubble Space Telescope detected a supernova that proved the universe had been expanding faster in the past. This acceleration was unexpected and challenged our understanding of the fundamental laws of physics governing the universe. The unexpected acceleration of the universe's expansion puzzled scientists, who proposed three possible explanations. One suggestion involved a revised version of Einstein's theory of gravity that included the cosmological constant. Another possibility was the existence of a mysterious energy fluid filling the universe. The third theory was that there might be something fundamentally incorrect with Einstein's theory of gravity. None of these explanations has been proven yet, but they have given rise to the name dark energy. Although much about dark energy remains unknown, scientists do know that it makes up roughly 68% of the universe, with dark matter accounting for around 27%. In contrast, all the matter that we have observed with our instruments, known as normal matter, makes up less than 5% of the universe. Picture this: billions of years from now, the universe will be a vastly different place. As galaxies continue to move away from each other, the universe will gradually cool down, leading to the burning out of stars and the scattering of materials necessary for star formation. This will eventually lead to a time where no new stars will form, and all light fades, resulting in a pitch-black sky. This bleak scenario is called heat death, and is based on the second law of thermodynamics. This law states that the total disorder, or entropy, in a closed system increases over time. As energy is transferred within an isolated system, it will eventually be evenly distributed throughout, resulting in maximum entropy, where everything in a system becomes uniformly disordered, and no more energy is available for work. The consequences are immense when we apply this concept to the entire universe. As the universe keeps expanding, its energy will disperse more and more, causing everything within it to cool down gradually. Ultimately, all the stars in the universe will exhaust their fuel and stop burning, leaving behind only lifeless, frigid remnants. The universe will have attained the maximum level of entropy, with its energy evenly distributed, and everything will become lifeless and dark. But this idea isn't new. It was first presented by Lord Kelvin, who challenged the scientific community's understanding of heat in the mid-1800s. Now, over a century later, we have a deeper appreciation of the full implications of his ideas. He proposed that heat was not a substance, but rather a form of mechanical energy. This idea revolutionized the field of thermodynamics and laid the groundwork for the second law of thermodynamics. In his famous 1852 paper on a universal tendency in nature to the dissipation of mechanical energy, Kelvin argued that mechanical energy, like the energy that powers our machines, naturally degrades over time. This concept piqued the interest of other preeminent physicists, including William Rankine and Hermann von Helmholtz, who engaged in a lively discussion with Kelvin about his theories. In 1862, Kevlin published yet another thought-provoking article on the age of the sun's heat, which sparked further discussion and debate in the scientific community. In his later work titled On the Age of the Sun's Heat, Thomson reaffirmed his belief in the conservation of energy and the universe's tendency for energy to dissipate. He argued that the second law of thermodynamics would result in a diffusion of heat, the cessation of motion, and the exhaustion of potential energy throughout the material universe. According to Thomson, this process would ultimately lead to the heat death of the universe, where all energy is uniformly distributed. While it is impossible to imagine a boundary to the universe's extent, the existing laws suggest an endless progression of action that involves the transformation of potential energy into palpable motion and then into heat throughout space. In such a scenario, the universe would not have a single finite mechanism that would eventually come to a stop, but instead an unending cycle of energy transformation. So far, the Hubble constant, which measures the universe's expansion rate, has not accelerated enough to tear apart galaxies held together by gravity. However, it is still strong enough to keep pushing everything further apart. But what if the acceleration rate continues to rise, hitting infinity? All physical objects in the universe, from tiny particles to massive galaxies, would break down into elementary particles and radiation. This breakdown would continue until the energy density, scale factor, and expansion rate become infinite, resulting in a singularity that marks the universe's end. It's a mind-boggling concept, but scientists are hard at work trying to understand the Big Rip and how it will shape the universe's ultimate fate. The scientific concept known as the Big Rip has sparked scientific research and debate, as it suggests that the universe's expansion will keep accelerating and eventually overcome the gravitational forces that hold structures like galaxies together. So, could it be that the universe is hurtling towards its destruction? Some scientists believe that the key player in this cosmic catastrophe is dark energy, which is causing the universe's expansion to speed up faster and faster. If dark energy continues to increase indefinitely, it could overpower gravity and destroy everything in the universe, including space-time itself. The implications of the Big Rip are truly catastrophic. It would be an apocalyptic event that would make even the most epic disaster movies look tame. The mere thought of galaxies and stars being stretched out and disintegrated into their component parts is mind-boggling. And if the force of dark energy grows strong enough to tear apart individual atoms, then we are looking at the end of the universe as we know it. The Big Rip would ultimately lead to the complete destruction of all matter and energy in the universe, leaving behind a void without any structure or significance. However, there is an opposing prediction, which suggests that the universe will eventually stop expanding and start contracting, resulting in the Big Crunch. This theory was initially proposed by Alexander Friedman, a Russian physicist who was developing a set of equations that indicated the universe's density would decide whether it would expand or contract. If the gravitational pull of the matter in the universe is more powerful than the explosive force of the Big Bang, the Big Crunch would occur. So, what would happen during the Big Crunch? Well, things would get pretty chaotic. The universe's expansion would gradually slow down until it grinds to a halt and starts collapsing in on itself. Galaxies would merge as space between them shrinks, eventually forming a single massive black hole that would devour everything in its path. The final moments of the universe would be a blazing inferno, radiating high-energy particles and starlight out in every direction. But it doesn't end there. As the universe collapses in on itself, it generates an incredible amount of heat and pressure, pushing the temperature to infinity. And when the collapse is complete, space and time, the very fabric of the universe, would cease to exist. The theory suggests that the universe may undergo an infinite cycle of expansion and contraction known as the Big Bounce, which means that a new Big Bang could occur. This means that there is still a chance for the universe to avoid complete destruction. But unfortunately, that's not the only scenario we need to worry about. There's also a terrifying prospect of vacuum decay, which could bring about the end of the universe. To understand this concept, we first need to explore the Higgs field, which could be in a stable state, but not the lowest one. The Higgs field needs to reach the lowest potential energy state to be stable and favorable, but it has not done so yet. There are two ways in which the Higgs field could potentially shift into a more favorable energy state, and neither one is good news for us. The first is through a high-energy event that propels the field over a hill and into the lower valley. The second is through quantum tunneling, in which a Higgs boson particle spontaneously creates a bubble of the more favorable energy state. If this happens, the bubble will expand at the speed of light, destroying everything in its path and rewriting the laws of the universe as we know it. As the bubble expands at the speed of light, everything in the universe will be annihilated. The terrifying thing about vacuum decay is that it could happen at any moment, with no warning. Although it is currently just a theory, the possibility remains that everything we cherish could be destroyed in an instant. Up until now, every scenario that has been presented is based on a simplistic version of the equation of state for dark energy. However, we know very little about the fundamental physics of this mysterious force. According to the theory of inflation, the early universe was dominated by a different kind of dark energy during the Big Bang. But since inflation ended, the equation of state for dark energy has become far more complex than what we currently assume for present-day dark energy. There's a chance that the equation of state for dark energy could change once again, which could have unforeseeable consequences. The possibilities for what could happen remain a mystery. Even though these outcomes are still theoretical, our scientific advancements have made our ideas about the universe's fate more precise, but the fact that we don't know for sure how it will end is a testament to the universe's complexity and beauty. With its vastness and age, the universe holds many secrets that challenges our understanding and pushes the boundaries of science to seemingly impossible limits. What are your thoughts on the future of the universe? Do you think there's something we're missing that could change our understanding of the universe's fate? With only a small fraction of the universe observable, there is so much we still don't know about the universe, and it's exciting to think about what discoveries might be waiting for us in the future. Share your thoughts in the comments below, and if you enjoyed this video, be sure to give it a thumbs up and subscribe to our channel for more captivating content about science and the universe. Thanks for watching.